Can you hear me?
Yes, I hear you. Yalla, you can
Okay.
start. Yalla.
Okay. So a quick overview of what we are going to be talking about. We will first give you background information and like from where this technology arised and what are the motives behind it. And we will be explaining the need for CCS in our current world. Then we will be moving on and explaining how does CCS really work and like the technicalities related to this technology. And finally, we will be mentioning some challenges and opportunities presented with that technology. So first off, background info. First, we all know that the world is witnessing an unprecedented growth, whether it being from increasing population rates to advancements in engineering, healthcare, science, economics, and all different fields. And this has led to an increase in life expectancy and a lot of health metrics like we are generally more healthy. We live longer than people who lived before us, like 500 years ago, and we live on average better lifestyles. However, there is a darker side of the story, and with this increase in the quality of our lifestyles, our healthcare systems, there is also an increase in energy consumption, and we heavily rely on fossil fuels for this energy consumption. And whenever we use fossil fuels to produce energy, we produce a lot of byproducts and mainly greenhouse gases. And these greenhouse gases are extremely dangerous for society because they lead to different human health problems, and they are bad for the environment as well. So the situation is not reassuring at all. Several studies has proved that pollution, which is caused by these greenhouse gases, cause millions of premature deaths due to cancer, cardiovascular disease, and a lot of other health issues. But not only that, the pollution that we induce into the environment is very risky and affects the planet overall, like not just humans. So now, why do we need CCS? We need CCS because first, CO2, which is one of the main greenhouse gases that are emitted, is causing a lot of harm in today's world. Some of its repercussions include climate change, pollution, and extreme weather. Climate change leads to increased temperature, pollution leads to smog and eventually acid rain, and extreme weather leads to wildfires and food supply disruptions and all things that are basically detrimental to society. Now, we really need CCS and we need it fast because, first of all, the IPCC has warned us that global warming is at alarming rates, and we should be limiting this global warming that we induced ever since the Industrial Revolution to only 1.5 degrees Celsius. Because if global warming ever reaches 3 or 4 degrees and surpasses it, this is where the real danger happens. So in order to limit this global warming to 1.5 degrees Celsius, we have to reach a net zero by 2050. These numbers are heavily studied and they are not just random numbers thrown out. We have to have net zero carbon by 2050 and negative 20 billion tons of CO2 per year by 2100. So by 2100, I mean. So these are not numbers to be taken lightly. And what the IPCC is basically suggesting is that we reverse the effect that we're doing. What we are doing and what we were doing is not normal. It took 650 million years for fossil fuels to form, and we could exhaust all of them in less than 200 years and not do anything to rectify our mistakes. So how do we achieve these negative emissions? Like, I know it may sound weird for some of you that, okay, how can we produce or emit negative 20 billion uh, tons of CO2 per year? Well, the answer is within our technology that we are talking about today, and it is carbon capture and storage. Now, there is naturally a way for carbon capture and storage to happen, and it is basically through photosynthesis. This is nature's way of capturing carbon. However, humans have disrupted the carbon cycle. There is too low plants because of deforestation, and there is too high carbon dioxide because of these new manufacturing and energy and consumption, as I mentioned before. So we are disrupting the carbon cycle, and we must do something to retrieve equilibrium back.
Okay, so I think I'll take it from here. We've been talking about CCS all along, but we don't really understand what CCS is yet, and I'll be explaining it. So, can you hear me, by the way?
Yes, we.
Okay. As the name implies, CCS means the capture of carbon and its storage. Understand it better, we will be following this roadmap that's on the screen. So first, we have to understand where the CO2 is coming from, and it's basically from the consumption of fossil fuels. Although we get useful products, there are some bad products, which is CO2, which we will be focusing on reducing. To do so, the carbon capture and storage method consists of 3 steps. First, the capture and the compression. Second, the transportation. And third, the storage. And I'll be talking about each step more in depth in order to understand the technicalities of each. So I think that we can get into the capture process and the compression. So there are 2 main ways of capturing the carbon. First, there's the typical CCS plants, which are basically net zero. So in these plants, there are 3 methods to capture carbon, either post-combustion, pre-combustion, or oxy-fuel combustion. And on the other hand, there are some net negative methods, which is the direct air capture, which is basically directly capturing the carbon from the air. So things will become clear as we go deeper into the process and the pros and cons of each of these methods. But before we do so, there are some definitions that we have to lay out. First, chemical absorption, which is used in most of these processes, and it basically separates the CO2 from the other gases by using liquid solvents or solid solvents like amides or ammonia. A second important definition is the energy penalty, which is basically the energy required for these systems that are being used. I'll be re-explaining these as I go further in the analysis and pointing out where they're at. So let's start with post-combustion capture. So as the name implies, we would be capturing the carbon after it being combusted. This is well described by the figure below. Fuel is actually burnt with the presence of air to create a flue gas. And the flue gas is undergoes chemical absorption in an absorber tower with a solvent. The products of this would be a solvent CO2 solution from one side and flue gas without CO2 from the other side. So the solvent CO2 solution moves ahead to the stripper tower, where it is heated and separated between CO2, which is collected and compressed, and the solvent, which is recollected and reused. So this would be the post-combustion process, and it's the most common process today. It allows to capture about 90% of CO2 and can be retrofitted to plants, which is very useful as it differentiates it from the other processes. Now, of course, there are some cons with it, and this is the high capital investment and the energy penalty, which is higher than 30%. So basically using that post-combustion process would be using 30% of the full facility's energy. Now let's move on to pre-combustion. Pre-combustion uses a different logic, which is basically taking out the carbon before combustion. And this might not seem very logical, but with this process, I hope it clears the ideas up a bit. So first, air is stripped from its pure oxygen, which reacts with fuel to create a syngas. This syngas is made up mainly of CO, CO2, H2O, and H. Basically, it has very little impurities and no nitrates. The syngas is mixed with steam in a shift reactor to convert CO into CO2 and H2. Now, this is the important part. So after getting CO2 and H2, we separate them by chemical absorption again, and the CO2 is collected and compressed, while the H2 can be used as a new source of energy. This is usually called blue energy, and it's an up-and-coming trend, but we won't go too much into details. So the main point is that we were able to capture the CO2. Now, the advantages of this technique is that it allows more than 90%. So with post-combustion, we get about 90%. With this one, we get more than 90% of CO2 capture. And there's also a significant advantage in the energy penalty, which is below 20%. However, the main problem with it is the high capital investment, and this can only be built simultaneously with the plant, unlike the post-combustion, which could have been retrofitted to already present power plants or industrial plants. So let's move on to the oxy-fuel combustion. The oxy-fuel combustion is basically a kind of spin on the post-combustion, where at first oxygen is separated from air, and then it reacts with the fuel to create a flue gas. Now, this separation creates a very pure gas, which is H2O. So there are no nitrates and there are very little impurity. Since it contains CO2 and H2O, no chemical absorption, and we can just use a condensator to separate the water and the CO2. Is someone speaking? Okay, so let's just continue. Moving on to the pros and cons. This oxy-fuel combustion, although it seems a lot more advantageous since it allows the capture of about 99% of the CO2 and very low nitrogen emissions, it's very high. It's high actually investment, making it almost impossible, a non-viable solution, as well as a very high energy penalty since the air separation unit is very demanding on energy. So now that we understand the CCS, the typical CCS methods, a new initiative that's very interesting, which is a direct air capture. Different since it consists of directly capturing the CO2 from the atmosphere. However, there are not many plants of this. So let's talk a bit about the process direct air tree that captures the carbon from the atmospheres and puts it into the ground. It works by large fans drawing in the air from the atmosphere and then stripping it from the CO2 by using chemical absorption with solid scrubbers, so basically filters. The filters are then heated to release the CO2, and by this we would have concentrated CO2 on one hand and filtered air-free CO2 on the other hand. This basically sums up the direct air capture. It also has its pros and cons. At very large scales, it would be very beneficial. However, today, a non-viable solution, and without governmental intervention, to be a very difficult method to go ahead with. So now that we sort of understand the first step of carbon capture and compression, to the other steps, which are transportation and storage. So transportation is sometimes undermined. People don't look a lot on it, but it's a very important step or increase the cost of a project. The most used transportation methods are through pipes and through a ship. And now focus too much on it and for carbon. So in order to understand how where to store carbon, there are a couple of steps. So how is CO2 injected underground? How is it maintained underground? What are storage sites? The best injected underground. So in order to put
Sorry,
in a super
it's Jad or Ghadi? It's
uh,
Jad or Ghadi?
Excuse me?
Is Jad or Ghadi talking?
Jad.
Jad, please
Meaning
ما
this
بعرف
right
عم
now.
بقطش كتير. Can you try to change your place or لأنه it's interrupting a lot.
He's clear. I think it's your connection, Professor.
That's fine.
It sounded very clear.
Okay.
Maybe it's from your side, Professor.
Okay, it might be. Yeah. Continue.
okay. So to be injected underground, the carbon has to be in a supercritical fluid state, which is basically the properties of a liquid and a gas, in order to take up the space. Now, this is naturally possible after a specific critical depth, where Earth has the pressure and temperature required naturally. Now that we understand a bit how CO2 is when it's injected, it's maintained underground by a couple of mechanisms. First, structural trapping. CO2 is injected, will go into the porous rocks, and since it's buoyant, it will float upwards. However, it will be blocked by a cap rock, which is non-porous rock, and this is what we call structural trapping. Now, at a more microscopic scale, so the lower we go in scale, other sort of mechanisms also happen. So we also have residual trapping, where the CO2 literally gets trapped between rock grains. And lastly, the final sorts of trapping are solubility and mineral trapping. So CO2 can get dissolved in brine water, which is the solubility trapping, and it becomes HCO3 minus. Over long periods of time, HCO3 minus reacts with magnesium to give MgCO3, which permanently holds the carbon in place as a solid. Now that you understand the trapping mechanisms, how can we decide on what site to use? So there's a lot of factors to take into consideration. First, we need storage space. And by this, we're not only considering the total volume, but we have to consider the volume within the porous rocks. So we only have the capacity within the pores. And we are going to need millions of meters cubed. Second is the injectivity. So how fast can we inject the carbon into the porous rocks? Third, and one of the most important ones, is the integrity. This field is very heavily regularized, and there's a lot of laws that are surrounding it, because any accident of leaks would be a major issue. So integrity basically consists of the sites having many protective layers. And lastly, depth. It's there in order to keep our carbon in the supercritical fluid state. Now that you know the criteria to choose a sites, let's talk about the potential sites that could be used in the world. So as we can see from this figure, there are a couple of interesting sites. So first, we can start reusing depleted oil and gas reservoirs. By that, we would have already prepared the infrastructure, so costs would be minimal. Another interesting idea would be deep, unused and water saturated reservoirs. There are a lot of ideas that could be done, like unminable coal seams and oil shales. But one interesting thing would be the use of CO2 in enhanced oil recovery. So sometimes in oil fields, there's a lot of oil that remains trapped underground that cannot be extracted. In this case, we could have the CO2 be introduced from one side and push the oil, which is on the underground well, from the other side. By that, we would be extracting the maximum capacity of oil, and we would be reusing a depleted reservoir. This is it for the technicalities of the carbon capture and process. I'll leave the place for Radi to explain the challenges and opportunities.
Radi?
Radi, we can't hear.
Is it better now?
Yes.
Now we can hear.
Yeah.
Okay. So what I was mentioning is that the reality of CCS is that it is facing a lot of challenges, and it can benefit from a lot of opportunities presented to it. So now that we know how CCS works and why do we need it, we should now assess the current situation of CCS. So first, there are only two direct air capture facilities in the world, and this is very low in order to achieve the IPCC 1.5 degrees. So we need to be on a more larger scale all over the world. And the most prominent challenges that are faced by CCS is first the huge cost associated with, the lack of financial incentives, and the lack of government support. First of all, there are a lot of costs encountered when someone decides to implement a CCS facility in their plant or other independent facilities. We all know that time value of money is considered because money has to be spent currently, and we all know that $1 worth today is worth less than $1 tomorrow, because the money that could be used in this facility can be invested otherwhere and yield interest and double and triple. So time value of money is important in these mega projects. Initial investment is huge, usually to set up the machinery, the facilities, to do the construction, to do research and everything. The capture process is costly because we have to set up and it requires energy to function. The transportation process is as well expensive. We have to transport this carbon that we captured and compressed. The storage process is extremely